Today to my class, and today is Tuesday, so I'm going to start chapter 3. And before that, I will just again revise the polyatomic ions. Okay, and also I will share the screen. Okay. So talking about polyatomic ions. So polyatomic ions are a group of atoms with some definite charges. At this point, we are not trying to learn how those charges came, okay? We are just trying to learn what are their formulas and what are their charges. That's it. Because we got to name them. We got to write their names and formulas. Okay. So I said there are total 14, but if you remember 12, you should be fine. So what are them? So you can classify them as +1, +2, +3 category. So that's how I memorize. What are the +1 charges polyatomic ions? What are the +2 charges? Sorry, minus. My bad. I'm talking about cations. -2, -3. There is only one +1 charge polyatomic ion, and that is ammonium ion. That is nitrogen H4 NH4 with plus charge, which is called ammonium. So -1, you get OH minus, which is called hydroxide. Then you get CN minus, which is called cyanide. Then you have nitrate, nitrite pair. Nitrate means higher oxygen, nitrite means lower oxygen, lower number of oxygen. Then we have chlorate, chloride, ClO3 minus chlorate, ClO2 minus chloride, just like nitrate, nitrite. Okay. There are several others. Oh, acetate, acetate. CH3CO minus, which is called acetate. This is the only organic polyatomic ion. CH3COO. Some people write it as C2H3O2. That is also you may see. Okay, same formula. 2 carbons written separately or 2 carbons written together. CH3COO or C2H3O2. Okay, so I got 1, 2, 3, 4, 5, 6, 7. Okay, 7 polyatomic ions, those are having -1 charge. Remember, this is only for test 1 I am asking to memorize. There are several others, and I'm not going into them. Like I can talk about perchlorate, ClO4 minus. I can talk about hypochlorite, ClO minus. Those are also very important. Okay, but I'm just asking you to know this much only for test 1. So that if I give you BrO3 instead of ClO3 minus, you should be able to write this is bromate. Or if I give you BrO2 minus, you should be able to tell that this is bromide, just like chlorate, chloride. Okay? Because we are just replacing halogens, chlorine with bromine or iodine like that. Any question about the -1 polyatomic charges? -1. No. And then -2. -2, there are again pairs, sulfate, SO4, 2 minus, 1 sulfur, 4 oxygen with 2 minus, sulfate, 1 sulfur, 3 oxygen with 2 minus, sulfide, and then carbonate, CO3, 2 minus, carbonate, and then we have pairs, like sulfate comes with another hydrogen added to that, HSO4 minus. This should be ideally in -1 block, but I did not write because it is just conjugate part of sulfate. So if you look at the difference between SO4 2 minus and HSO4 minus, what do you notice? You notice that we add one hydrogen to SO4 2 minus, and the charge is reduced by 1. So instead of 2 minus, now we have 1 minus. So same way you can write for sulfite. You can write HSO3 minus. Okay, they are like conjugate pair of sulfite. Yeah? So just remember that when you add hydrogen to the sulfate or sulfite, charge decreases by 1 unit. Instead of 2 minus, it becomes 1 minus. Okay? And then phosphate minus 3 is only phosphate, PO4 3 minus. So this is, sorry, this is called phosphate. If you remember this is enough for now. For now, this is enough. Okay. And later we will add more here with the 2 minus. Like Cr2O7 is called dichromate. These are extra again. CrO42 minus is chromate. Okay. So dichromate, chromate, you need to know that. Okay. So with -1, you need to know MnO4 minus, which is permanganate. Okay. So this is like extra category. If you know, very good. With phosphate, you can write H2PO4 minus dihydrogen phosphate, HPO4 2 minus. You can write hydrogen phosphate. Okay. Like this. So the box on the right hand side are extra, but these ones are required. Okay, this is the required box. Any question?
No, ma'am.
No? Okay, so let's just do 1 or 2 practice. So what do you think? What is the name of, can you tell me the name of copper? Sorry, I told. Okay. 3, 2. What should be the name of this compound? Okay, so copper is transition metal, right? Let me see the chat window first. Is anyone? No. Okay. So copper is transition metal. So we got to figure out the charge and write in the name. So NO3 looks like nitrate. If you look at the charge, NO3 is nitrate. It has charge -1. So this guy, NO3, has charge -1. So again, if you don't know the charge of the metal, put a wall in between metal and non-metal and try to figure out the charges separately. So NO3 has -1 charge and there are 2 of them. So the total negative charge is -2. So that must be balanced by this copper. So copper should have charge +2. So the name should be copper 2 within parenthesis in Roman numeral nitrate. Okay. Can you tell me the formula? Formula of ammonium sulfate. What is the formula of ammonium sulfate?
NH plus.
Yeah, ammonium, you know, NH4 plus and sulfate
SO4
4 2 minus. So now you see their charges are different. So that means when you write the formula, you have to switch their charges. So ammonium will get the charge of sulfate and sulfate will get the charge of ammonium. Okay. Now what should I write? NH4. And then how should I write this 2? You have to put a parenthesis and then 2. You cannot just write 2 hanging from NH4. Okay. So you have to put a parenthesis and then 2 and sulfate. Because it is getting charged 1 plus, so we don't write 1, so it is fine. Are you guys okay?
Yes.
Okay, one last. What is the formula of magnesium phosphate? Sorry, I cannot see that. Okay, no. Okay, magnesium. Magnesium is where? Where this metal is? The main group or transition metal? Is the magnesium main group metals or transition metals?
The main group.
Main group. So you know the charge. What is the charge? Magnesium is in group 2.
Plus.
So plus 2. Very good. And phosphate, you just know from the chart above, phosphate has minus 3. Now how you are going to write? You have to switch their charges because they are not equal. So when I switch, I write Mg3, then PO4. How should I write 2?
Parentheses 2.
Parenthesis 2. Very good. Okay, so now you practice. You practice this type of writing. So you know for transition metal, you have to write charges, not for the main group. Now main group means group 1, group 2, 3, 4, 5, 6, 7. Those are the main group. And then you have to know the polyatomic ions. You have to know the negative charges from the periodic table, main group, like chloride, bromide, iodide, sulfide, oxide, like that, nitride, phosphide. And they always, monoatomic ion always end up with, monoatomic means main group nonmetals. Anions always end up with last name with ide, IDE. So you take the stem name and then you add ide. Okay, add to their name. And you already know the covalent compounds. So I already discussed yesterday covalent compounds. So you practice writing covalent compounds. What is the name for, let's say pH3? What is the name for NH3? Do you guys know what is the name for NH3? What should be the name if you follow the nomenclature rule? What should be the name?
Ammonia.
Yeah. Normally, students tell that, oh, it is nitrogen trihydride, but that we don't use. We use the name ammonia. Very good. Like water. So water normally people should say that, oh, it is dihydrogen oxide, but nobody says dihydrogen oxide. We say water. And another rule I told you that always the element which is first, and that should be from the further left element on the periodic table. And anything that on the right hand side should be the element that is more to the right hand side of the periodic table. Okay, that is our rule. But sometimes you see exception, like ammonia, you see hydrogen is after N. Okay, whereas hydrogen should be before N. Okay, so those type of things happen sometimes. Okay, and then acids nomenclature also I discussed. So people should know how to name acids, binary acids and oxo acids. Binary acid means you have only HCl, Br, like that, H2S. Okay? or oxoacid means when you have polyatomic ion like nitric acid, nitrous acid, sulfuric acid, where you have oxygen. You don't mention hydrogen, hydro. So if you just practice, then it should be fine. Okay. Any questions so far? No question? Okay. So I can start chapter 3. So chapter 3 means we have to talk about moles and molar mass. Okay. So we will open the presentation. Again, I'm sorry, my webcam is not working. Okay. So, but you should be able to see the screen and everything. So what we are learning in chapter 3? Chapter 3 is very small. That's why I included that in your test actually, because it is like only 4 topics you have to learn. So first thing that we are learning, formula, mass and mole concept. Then determining the empirical formula and molecular formulas, which is very, very important. And then molarity and dilution along with that, and other units of concentration. Okay? So the first thing is formula, mass and mole. So mole, I think everybody is familiar with the term mole. So today we are just going to know more in depth, okay? Chemical definition of mole, what is, how you use that. So we define mole. People think that mole means some, I don't know, the something on the skin or something like that. Okay, but we define mole as unit. Okay, mole is actually in chemistry, it is defined as one of the units that represents the collection of a very large number of particles. So if you have 6.02 times 10 to the 23 particles, particles means atoms, molecules, ions, that collection of particles should be called 1 mole. Okay. So I definitely would like to show you this video. I don't know if I can copy this and then paste it here. So this is a very nice overview of what is mole. Okay.
That feeling when, yep, they've eaten everything. Keep them full with Hot Pockets, premium pepperoni, real cheese, and that buttery garlic crust, literally built to satisfy. Hot Pockets!
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you had equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amadeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container, or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you'd use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is, anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Did you guys like that?
Yeah, it's nice.
Okay, thank you. Yes, I somehow there are so many videos on mole, but this one I like. Okay. So what the video says that mole is actually unit. Okay, this is one unit when we take a very large number of particles, because we want to calculate. A chemist, just like you saw that in last chapter we were describing the periodic chart, but we also want to calculate the number of atoms that we are taking for chemical reaction, on the number of molecules that are participating in chemical reaction. So when we take the number of molecules or atoms, when we try to calculate, they become a very large number because atoms are very, very small. Molecules are very, very small. So it is hard for us to describe like, okay, I have 10 million molecules here. Out of the 10 million molecules, 5 million molecules reacted. So that is not a very convenient way. So that's why we widely use this Avogadro number and mole concepts to use calculations in our chemistry, okay, stoichiometry. That we call, okay, stoichiometry means the branch of chemistry that deals with the quantity in chemical reactions. And for that, we use the unit called mole, okay. So 1 mole means 6.02 times 10 to the 23 atoms, molecules, or ions. Anytime you can take that, okay. And it is also defined as the number of atoms present in 12 grams of carbon C12 isotope. Okay, so if you take 12 grams of carbon 12 isotope, oops, one note. So if you take 12 grams of 12 carbon, the number of atoms present is called 1 mole. Okay, so you see the definition of 1 mole is MOLE, but when you write the unit, we just drop the E. Okay, we just write MOL. Okay, that is another thing you may notice. Okay, definition contains E, but not the unit. So how do you know this is 12 gram for carbon? How about other elements? That's the question comes on our mind. So there is a very convenient way to know that, and that is the periodic chart. So if you have periodic chart with you, okay, I cannot show you on the screen today, okay, because of my webcam problem. But if you have the periodic table with you, you can see that there is atomic mass provided in each box of the periodic table, right? Hydrogen is 1.00794, helium is 4.0, lithium is 6.941. So basically what they represent? They represent average mass of one single atom of lithium. So if you take one tiny lithium atom, that should weigh 6.941 mu. Okay, that is the meaning. Now, there is a very interesting connection between this AMU and the mole. It has been found that if you take 6.0 times 10 to the 23 atoms of lithium, then that AMU becomes 1 gram. Okay, so that means if I take 1 mole of lithium, that should weigh exactly same 6.941, just like given in the periodic table. Now I'm not going to use AMU. I'm going to use the unit mole, 1 gram. Okay, so what I mean by that, that is called molar mass of lithium. So if you take lithium, for example, I'm taking any one element, you can take other element. Lithium, if you take one atom, it should weigh 6.941 mu, which is a very small unit. If you take lithium 6.02 times 10 to the 23 atoms, which is 1 mole of lithium, that should weigh exactly same number, 6.941, but your unit is gram. Okay, so what do you understand? We understand that 1 mole of lithium is equal to 6.941 grams, right? If you take 1 mole of lithium atom and weigh on the balance, it should weigh 6.94 gram. So 1 mole of lithium means how many lithium atoms? That means a large, very large number of atoms. That is equal to 6.02 times 10 to the 23rd. Okay, I cannot even write here, like it will continue like this. Okay, so it will continue. That many atoms should weigh 6.941 grams. Everybody clear with that?
Yes.
Question? No question. So yeah, please make sure that you understand the difference, okay, between what is given on the periodic table versus what is mole versus what is atomic mass. These are very fundamental things. So there is another term called formula mass and molecular mass. So what is formula mass? Formula mass means mainly when you use the ionic compounds. So it is the average atomic masses of all the atoms. See, atoms. So when they say atoms, that means they're talking about one atom, two atom. So the unit should be AMU, right? Because atoms are tiny, very small. And then covalent molecules, they exist as discrete molecules. So when we calculate the formula mass of covalent molecules, that should be mainly called molecular mass. So in short, if they ask you to calculate the formula mass, you calculate the same thing, you write the same thing from the periodic table, you just mention the unit AMU. And if they tell you determine the molecular mass or molar mass, you write again the same thing, but now you mention the unit gram. Okay, so I'm going to go show you some examples. See, this is our calculation. Okay, yeah, this is carbon, hydrogen, chlorine. So if you take one carbon, one hydrogen, one chlorine, so the average atomic mass, which is provided on the periodic table for carbon, is 12.01. You multiply that by 1. Hydrogen, again, 1.008. And chlorine is 35.45. Now, one thing I get many questions from the student, like they ask me how many significant figure we should take from the periodic table. You just know that you can take minimum, you should take minimum 4 significant figure. See all these digits, they all have 4 minimum significant figures. It does not mean that you only take 4, but you should take minimum 4, okay, to calculate. And then if you take 12.01 plus 1.008 plus 106, okay, because there are 3 chlorine, you multiply by 3, and then you take the sum of 1 carbon, 1 hydrogen, and 3 chlorine, then you should get the molecular mass 119.37. And that should be the sum of all the average atomic masses. Is it okay with everybody? Question? So again, there is another problem. So you are given C9H8O4, which is the formula of aspirin. You know aspirin, which is the anti-inflammatory or pain reducing medication, okay? Fever reducing medication. So how do you know what is the average molecular mass of this? So you just take the 1 carbon, since there are 9 atoms, so you multiply by 9, the mass of 1 atom. Okay, that gives you 108.09. Then hydrogen, since there are 8 subscript, that means there are 8 atoms of hydrogen. You take the 1.008 value from the periodic table, multiply by 8, which is 8.064. And then the next element is oxygen. You take 4 atoms of oxygen and you take the average atomic mass, which is 16, multiply by 4, you get 64. Now you take the sum of all the elements atomic mass values, and that should give you the molecular mass or the molar mass of the aspirin. So you can calculate anything like this. Okay? So as I said before, for ionic compounds, normally we say the term formula mass, and for molecular compounds or covalent compounds, we use the term molecular mass. Okay. Question. Like sodium chloride, we use the term formula mass, okay, because this is ionic compound, but they are same, and the same operation that you are doing as you did before. But in this case, since it was all non-metals, it was covalent compounds, so that's why we use the term molecular mass. Okay, they mean same, but we use 2 different terms. So can I ask you to calculate the molar mass or the molecular mass of water? What is the molecular mass of water? Oh, okay, so it is easy. If you need to keep the periodic chart with you. So hydrogen 2, oxygen 1. So hydrogen
18.
Yes, very good. 1.008 times 2, which is 2.016 gram. And then oxygen is, if you look at the periodic table, the value is 15.99 on my periodic table. Times 1, which is 15.9998. So you just take the sum, it should give you 18.02. 2.016 plus 15.9998, so 18.015. So I'm getting 18.02. As I said, it should be minimum 4 significant figure. So what is the unit? Unit should be gram per mole. Remember, we are trying to calculate the mass of 1 mole of a substance. How much does it weigh? If 1 atom weighs this much, then what is the mass of that large number of particles that we call 1 mole? Okay. So this is called molar mass or molecular mass. Two things, okay? We just learned what is mole. Mole means a big collection of particles. It is just unit, another unit to define and 6.02 times 10 to the 23 particles. And then finding the mass of that many particles. How do you know what the mass of each element of that number? So we know that for hydrogen, it is 1.008. For oxygen, it is 15.9998 because each element weighs differently. And when they are combined in a compound, you just calculate like this. Look at their formula, multiply by their subscript, take the sum. You should be able to get the mass of 1 mole of that compound. That we call molar mass. Question, guys? Any question? You understand clear? Okay, nice. So this is the sig fig. If you see the Avogadro number sig fig, 6.0221417 actually. But we just use 3 significant figures, 6.02. Okay. The masses of 1 mole of different elements, however different, and the masses of individual atoms are drastically different. Okay. So this is just to give you one idea about how the amount looks like different, although they all represent the same number of particles. That means 1 mole. So if you look at the zinc atomic mass is 65.3. That means one mole of zinc should weigh 65.4 grams. And that's what you are seeing on this pellet. Okay, you are seeing that on this small dish, there are 65.4 grams of zinc are taken, and that is actually 1 mole, which has same number of atoms, just like the next one, and that is 12 grams. Okay, because it is a different element, so it weighs different. And that is the same number of atoms as you see on the bottom, 32.1 gram of sulfur. Okay, so everybody has the same number of particles, which is 6.02 times 10 to the 23. But they all weigh differently because atoms are different, elements are different. Okay, so molar mass we just understood. Okay, mass in grams of 1 mole of a substance, and the unit is gram per mole. Okay. So here you again they are showing that 1 mole of compound of element. So you see that 130.2 grams of this compound, okay, octanol, and then you see mercury 2 iodide, okay, 454.9 grams. And then also you see 32.2 grams of methanol. Okay, they are all 1 mole. So whether it is compound or element, they all should have same number of particles. In case of compound, we count the molecules. In case of element, we count the atoms. But the number is same, that is defined by 1 mole. Clear? Question? So here are some examples. Okay. So if you just assume that how many particles are actually 1 mole, this is a single droplet of water, which is roughly 100 billion times greater than the number of people on Earth. Okay. So how many moles are there here? You can imagine. Okay, so the relationship between the formula mass, the mole, and the Avogadro number can be applied to compute different quantities. Okay, so first one that we are converting, you see grams to moles. Okay, if you are given some grams, can you convert how many moles? So this is our problem. According to the nutritional guidelines from US Department of Agriculture, the estimated average requirement for dietary potassium is 4.7 grams. What is the estimated average requirement of potassium in moles? So let's say if somebody, it is not easy to define everything by mole always because it is counting unit, right? So counting is not always possible because atoms are so tiny. So most people conveniently use the grams unit. Now, sometimes we may have to know that this many grams means how many moles actually. So that's why we do this conversion. I told you before 1211 is all about equation solving and converting units. That is our story, okay, in terms of math. Either you have to convert from one unit to another unit, or you have to apply some equation to solve problems. So grams to moles or moles to grams. Moles to grams or grams to moles. Your conversion factor is always molar mass. Remember that. This is how I learned stoichiometry. So whenever I'm given moles, I have to convert grams. I will use the conversion factor as molar mass, given the problem. What I have to go, from moles to grams or grams to moles. Whenever I'm given moles and I have to convert to atoms or vice versa, or molecules, atoms, molecules, or ion. Sorry. Atoms, molecules, or ions, I will use the conversion factor Avogadro number. Again, based on the problem. So if I'm given moles, I have to go atoms, I will use Avogadro number. If I'm given atoms, I have to go moles, I will always use Avogadro number, and I will flip the ratio accordingly. Okay. So first problem we are solving. So we are given 4.7 grams of potassium. The question is how many moles is that? So you write what you are given. Given 4.7 grams of potassium. And what is needed? Number of moles. And I know that grams to moles means the conversion factor must be the molar mass. So what is the substance here? Substance here is K. So what is the molar mass of K? So we just need to look up the periodic table and find the molar mass from the periodic table. So potassium, I see potassium's molar mass is 39.0963. So molar mass of potassium is 39.0963 gram per mole. So I will always write 4.7 grams first. And then since I have to go to the mole, I'm going to write 1 mole on the top. That is my target. And the grams on the bottom, which is 39.0963. So I'm getting 4.7 divided by 39.0963, which is 0.120 moles of K. Now, since there are two significant figures, so I'm going to write, sometimes it goes 0.12 moles of K. Question. Everybody is able to do that?
Yes.
Yes? Very nice. Question, guys. If you have any question, you can ask me. So next one is just reverse. So reverse means you are given mole, you have to calculate the mass. So it says a liter of air contains 9.2 times 10 to the minus 4 moles of argon. What is the mass of argon in a liter of air? So again, same way, you set up. I prefer to write like that. I always write what is given and what is needed. Did somebody say something on the chat window? Can we do another one? Yeah, I will do many. Okay. So our given is 9.2 times 10 to the minus 4. 9.2 times 10 to the minus 4 moles. And I have to know the grams of air. So it is mole to grams basically. So I have to use the conversion factor molar mass. Okay. So argon, sorry, not air, sorry, argon. Argon. So what is the molar mass of argon? Your periodic table is your source. Look up the periodic table. I see argon got molar mass 39.948. So molar mass of argon, 39.948 gram per mole. So start with what you are given, 9.2 times 10 to the minus 4 moles of argon. Then I have to go to the grams, remember. So my grams should be on the top. So 39.948 grams should be on the top. And 1 mole argon would be on the bottom. So that mole will cancel out diagonally. And you will be getting 9.2. And then if you have my like calculator like TI-30 series, what I'm using, my calculator, then you may press EE and then -4. That should give you the exponent. And then multiply by 39.948, which is 0.03675. 0.03675 grams of argon. Again, how many significant figure? 2 significant figure is in your problem. So your number should be 0.037 grams of argon. Question. You guys are quiet today. Okay. No question. So this is grams to moles. I have, yeah, okay, yeah, go ahead, unmute and talk. Please unmute yourself and talk.
You said that it's 2 significant figures. So
Yeah.
are you saying that the 0 after the decimal doesn't count because it's
Yes, yes,
9.2?
of course, it is insignificant.
Okay, got it.
Yeah, because it is leading zero, so leading zeros are never significant. Anything left to the first non-zero digit is not significant. Okay. So now we are going to use the second conversion factor. Remember our second conversion factor was, if you want to, this is first one we just did, and this is second one, moles to atoms, atoms to moles, okay? Or moles to molecules, molecules to moles, okay? So let's say I ask you, how many molecules are in 5.83 moles of water? Okay, if that is your question. Molecules. Okay. So what is given? Given is 5.83 moles of water. And what is needed? Needed is molecules of water. Stoichiometry has a beauty. You know what is the beauty? Beauty is there is only one route. You cannot take different routes. So just you have to know what conversion factor you need to convert what. That's it. And then everything will fall into place. So moles to molecules. So what is our conversion factor? Should be Avogadro number. So you start with what you are given, 5.83 moles of water, and then multiplication sign, and then you write the ratio. What should be written on the top? What should be written on the bottom? Since we know that 1 mole means 6.02 times 10 to the 23 atoms or molecules or ions, since we are taking compound, we should immediately write it as molecules, because the fundamental unit of a compound is a molecule. Water is a compound because it is made of 2 or more elements chemically combined. So we need to go to the molecules, remember? So our molecules will be on the top. 6.02 times 10 to the 23 molecules on top. And 1 mole water on the bottom. See, we are writing this relationship as a conversion factor. Okay. So moles should cancel out. You should get 5.83 times 6.02 times 10 to the 23 molecules of water. So that means 6.02 times 5.83, 35.0966 times 10 to the 23 molecules of water. Now, since I'm from old school, how I do calculation, you know, I separate out. Let me show you. Where are my inks? Draw. See, I separate out the numerical part from the exponential part. I do this calculation separate, this calculation separate, and then I figure out the sig fig. So since I'm starting with 3 significant figure, I should write in 3 significant figures. So that means 35.1 times 10 to the 23, and then I write scientific notation. So I bring this decimal place over here, 3.51. And since I'm moving to the left, I have to multiply by 10. So it should be 3.51 times 10 to the 24 molecules of water. Any question?
No, ma'am.
Yeah. Oh, very great. So you guys are getting there. This is one of the toughest concept in Chem 1. Okay. So if you guys okay with grams and moles on the very first day, that's a very good sign. I must say that. Okay, so now we can go a little more advanced. So I can use the mass and I can ask you calculate the atoms. So your approach should be 2 conversion factors. Mass to moles, moles to atoms. Does it make sense? Because we cannot get mass to atoms directly. We have to go via moles. So mass to moles conversion factor, molar mass. Moles to atoms conversion factor, Avogadro number. Okay. So we are doing 2 steps conversion factor now. So let's say this one. So you are given 28.35 grams of glycine. Okay. Glycine has a formula like this, C2H5O2N. So you calculate the molecular mass of glycine and then you convert the grams to moles using the molar mass as a conversion factor. Okay. So 1 mole on the top and molar mass on the bottom. So that grams will cancel out and you get the moles. Okay. And then in the next step, they are asking how many atoms. So how do you do that? Sorry. So first you calculate the grams to moles. Yeah, this is a separate problem, I think. Yeah, this one you can look. Because this is not going to the atoms. I may ask you how many molecules are there. So then you have to multiply this by the Avogadro number. Okay, so let's rewrite that. Since I showed you the problem, I'm gonna write here so that you solve. So how many molecules are present in 28.35 grams of glycine? See, you are given grams, you have to find the molecules. So what should be, excuse me.
Bless you.
Thanks. What should be your approach? Your approach should be grams to moles and then moles to molecules. See, we did separately grams to moles. We did separately moles to molecules. Now they are combined together. Yeah. So glycine, we need to know the formula in order to find the molar mass to go to moles. So glycine formula is provided here. Where is the glycine formula? C2, okay. C2H5O2N. 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 So if it is C2H5O2 and N, how do you find the molar mass? So for C, if you look up the periodic table, the molar mass is 12.01. And that should be multiplied by 2 because it is C2. So it is 24.02 gram per mole. And then CH5. H5 means hydrogen 1.008 times 5. So you are getting 0.008 times 5. So 5.04 gram per mole. Then O2 should be 16 point, mine is 15.9944. Some periodic chart, they round it off, they write 16.00. So 15.9994 times 2 is 31.9988. And then one nitrogen itself is 14.0067. So it is 14.0067. So if you take the sum, what do you get? 24.02 plus 5.04. 24.02 plus 5.04 plus 31.9988 plus 14.0067. So 628, is it the one that you are getting?
I got 75.
75? I don't know my calculator. It is 75, right, right. So yeah, my calculator is wrong. 31.9988 plus 14.0067 plus 5.04 plus 24.02. Absolutely. 75.0655. So 75.07 gram per mole. Okay. So that is the molar mass. So let's convert the grams to moles first. So 28.35 grams of glycine, which is C2H5O2. So since I'm going to go to the mole, I'm going to write mole on the top over 75.07 gram. And then moles to molecules. So that means if I'm going to write the molecules on the top, 6.02 times 10 to the 23 molecules, and 1 mole on the bottom, 5O2N. So mole should cancel out, grams should cancel out. At the end, you should get molecules. So 28.35 over 75.07 times 6.02 times 10 to the 23 molecules of glycine. So you may calculate this number to get the final answer. Question? No question? 75.07 times 6.02, 2.27. Tell me if I'm wrong. Times 10 to the 23 molecules of glycine. Did you guys get the same number?
Yes, ma'am, I did.
73. Anybody?
Yes, I got the same one.
Okay, very good. Okay, now the last part, I'm just going to finish it up today. So if you look at this problem, it says a packet of artificial sweetener, 40 milligrams of saccharin. You all are familiar with saccharin. It is artificial sweetener. and which has the structural formula this, okay, C7H5NO3S. This is all organic compounds, you see. They are all annotation. Given the saccharin has a molar mass 183.18 gram per mole, how many saccharin molecules are in 40 milligrams, not grams, sample of saccharin? How many molecules? So you can easily do that the way we did, grams to moles, moles to molecules. The question is how many carbon atoms are in the sample? Okay, how you do that? How many carbon atoms? Okay. So since I am annotating, that means I can write here, right? Let me see. So the first part, no, sorry, I have to use, no, it does not let me, okay? I'm sorry, I cannot annotate on this PowerPoint.
Oh, sorry, I clicked by mistake. Maybe let me go back.
Okay, that's okay. I have to use my writing pad, OneNote. Okay. Hold on. It got froze, I think. Yeah. So you are given the saccharin C7H5NO3S, and molar mass is 183.18. So molar mass of C7H5NO3S. C7H5NO3S is 183.18, okay, gram per mole. So question is how many, remember we are doing molecules only, you can do only atoms for element, okay, just telling you, if you are asked to calculate the atoms, you can do the same thing, but that should not be the molar mass of the compound, that should be just the molar mass of the element. How many molecules are present? In 0.040 grams of saccharin C7H5NO3S. I think first part I will leave up to you. I hope you guys can do that. Grams to moles and moles to molecules. The second part I will show you how many carbon atoms. How many carbon atoms are present. Okay, so how do you know how many carbon atoms are present in that many grams of the compound? So here is our question. Our formula is C7H5NO3S. What does this subscript means to you? Now we know that they mean number of atoms. So this is basically microscopic picture. If you take, this is a compound. This is not an element. Several elements are combined together. So this represents one compound. But microscopically, if you go to the tiniest picture of that, this represents one molecule, right? One molecule of C7H5NO3S should have 7 atoms of carbon, 5 atoms of hydrogen, 1 atom of nitrogen, 3 atoms of oxygen, and 1 atom of sulfur. That is the description you have. Now, if you convert one molecule to 1 mole, you know what happens to these numbers? These numbers immediately gets transferred into moles of that element. So you can say that 1 mole of C7H5NO3S should have 7 moles of carbon, 5 moles of hydrogen, 1 mole of nitrogen, 3 moles of oxygen, and 1 mole of sulfur. Okay, that's how they are combined in 1 mole. Okay, the elements are combined because everything you are thinking in terms of Avogadro number now. That means you are multiplying everything by 6.02 times 10 to the 23. So if you take one molecule, instead of one molecule, if you take 1 mole, then all the atoms, number of atoms are also multiplied by Avogadro number, and they become moles. Okay, so now we have to just know how many moles are there, 0.0400 grams. Then we can use this relationship, right? So you just start given 0.0400 grams of C7H5NO3S. And what is needed? Number of atoms of carbon. So what is our path? Our route is convert grams to moles. Then moles of C7H5NO3S to moles of C. Just by looking at the subscript, okay? Just from the knowledge given in the problem. No calculation. And then if you know the moles, then your door is open. So moles to atoms, you can apply Avogadro number. So I'm going to take first 0.0400 grams of C7H5NO3S. Then I'm going to convert that to moles. What is my conversion factor? Of course, molar mass. So molar mass already provided. I'm going to write 1 mole C7H5NO3S on top. And the molar mass, which is 183.18. Okay. 183.18 grams of C7H5NO3S. Grams should cancel out. Okay, you should get the moles, and then you write 7 moles of C are present in 1 mole of C7H5NO3S. Make sense? Because I want to go to the moles of carbon from moles of C7H5NO3S, which is my compound. So then this should cancel out this. Yeah. And then once you have the moles of carbon, then we can write the Avogadro number. So 6.02 times 10 to the 23 atoms of C is equal to 1 mole of C. So what am I getting at the end? I'm getting 0.0400 divided by 183.18 times 7 times 6.02 times 10 to the 23 atoms of C. Are you guys okay, or do you have question? Because this is very, very important, okay? Everything is built on this part for next 2-3 chapters. If you understand moles, then you understand almost half of the CHEM 1 part. And then other half is the atom configuration and everything. So 0.0400 divided by 183.18 times 7 times 6.02. So I got 0.2300 times 10 to the 23 atoms. So if I write in conversion, I mean, how many significant figure? 3. So I have to write 2.30. If I move the decimal place to the right, that means I have to divide 10 to the 22 atoms of C. Did you get the same number, or my calculator is again wrong?
I can check it.
Times 7 times 6.02. Yeah, it is giving a different. I don't know. This is probably it is running out of battery, so I'm getting something different this time. 0.04, I'm sorry, very sorry. Divided by 183.18 times 7 times 6.02. Yeah, 00920 I got.
I got 9.2018.
Yeah,
2.
times 10 to the 23, that means 9.20 times 10 to the 20, right?
Hold on 1 second. Okay, now I got. Is that 0.0400?
0.0400, yes, correct.
0.00. I got 5.25.
I got 9.20 times 10 to the 20. Anybody else?
Something different.
Slightly different?
Mm-hmm. Okay,
How-
so 0.0400
Yeah,
times 7 times 6.
times 6.02 10 to the 23 over 183.18.
I think it's 9.20 times 10 to the 20. That's what I got.
Okay.
Okay, now I got. Yeah, I got that one.
Okay. Very good. So any question, guys? Did you follow? Any comments? Yeah, you can also tell me if you have anything here to add, or what do you feel about this? So the trick to succeed in summer course is that every day you learn something, small amount, even it is small, but you learn something and work on that. So I would highly encourage you to complete the chapter 2 quiz and move on to chapter 3 and complete the assignment for moles and molar mass today. And then tomorrow again, I'm gonna start doing the empirical formula, okay, stuff like that, next part. And then again, you guys will go and complete the homework. And then once I finish chapter 3, then you guys will take the quiz on Friday, Saturday, okay, something time like that. So that on Sunday or Monday, you can take the test. So this is how you don't put together everything on one day. That is too much stressful. So if you just learn a small piece every day, okay, and then you work on that, and you also retain the knowledge better. That is my opinion. Okay, so I'm gonna start this tomorrow, but do you guys have any other problem you like to solve at this point? Anything? Do you like to solve in front of me so that I can correct like this problem, or you guys like to try at home and then tell me? Like I definitely want you to solve this one. Okay, if I were in class, I would ask you to solve this one in front of me so that I make sure that you guys are getting. But since it is online, it is up to you. Okay, so if you like to do this, please do that. Okay, I'm here, I can correct you. And if you like to try at home, that is fine too.
Can we try it here and then
Yeah,
and to
please.
see if we might get it wrong?
Yes, that's what I want to correct you if you are wrong in any case. Yes. So please do that. How many C4H8 molecules are contained in 9.213 grams of this compound? And how many hydrogen atoms are there?
So we would first start from, since we're going to atoms, we have to start with the gram and we have to convert that into moles.
Yeah, but the first part is how many molecules. So you are going from grams to moles and moles to molecules. Because look, you are given the grams of this compound, C4H10, and they are asking how many molecules are there. So go from grams to moles of this compound, because this is the molar mass you have to find, and from moles to molecules. And then atoms is for hydrogen only, remember. It is not for the whole entire molecule. So how many hydrogen atoms are present in that many moles or in that many grams? Do you see the difference? Hydrogen, hydrogen is just a component of that molecule. So first we need to find the molecules from the grams. So we need to know the grams to moles, moles to molecules. So grams to moles means we need to find the molar mass. So my question is, can you calculate the molar mass of C4H10?
So 12.011.
Yeah,
Mhm.
times
4
12.0 times 4. And then
and
plus
then plus 1.008 times 10.
10. Yes, very good. How many moles?
58.124.
4 times 12 is 48 plus 10 times, yes, 58 something. So 9.213 grams over that number. And so what did you get? 9.213 divided by 58.08. I got 0.158 moles.
Me too.
Same, and then you multiply by Avogadro number to get the molecules.
Mhm.
So I got 9.517 times 10 to the 22. They have 9.545. Did you guys get 9.517 times 10 to the 22? Okay, shall I show here? Let me show. So I'm doing molar mass first. Molar mass of C4H10. 4 times 12.01 plus 10 times 1.008. So I'm getting 58.12 gram per mole. So that is the molar mass. I'm given 9.213 grams. First, I'm going to convert to mole. Okay. And then I'm going to convert the moles to molecules. So I'm getting 9.213 over 58.12 times 6.02 times 23 molecules. So that gave me 9.545 times 10 to the 22 molecules. Did you guys get?
I got the same thing. Yes, ma'am.
Yes.
Okay. So now this is my first part done. The second part is how many hydrogen atoms. So that means they are talking about one of the element in the compound. So then I have to look at the subscript to find the relationship. So I just found that from the formula, 10 moles of hydrogen is equal to 1 mole of C4H10, because the formula is C4H10. So there must be 10 moles of hydrogen in 1 mole of C4H10, and that's the relationship we are going to apply here. So again, I will start with what I'm given, 9.213 grams of C4H10. I have to convert that to mole. Without mole, you are not going anywhere. 58.12 grams of C4H10. And then once you get the moles of the compound, you apply this relationship. 10 moles of hydrogen over 1 mole of C4H10. Okay, so you get the moles of hydrogen from moles of C4H10. This is the point you apply. Okay, this is the point you apply. Because you got to know how many moles of one element are present in the moles of the compound. Okay? And then you continue. You write 6.02 times to the 23 atoms of hydrogen is equal to 1 mole hydrogen. So I'm getting almost the same number, 9.213 over 58.12 times 10 times 6.02 times 10 to the 23 atoms of hydrogen. So only difference is I'm multiplying by 10. Okay, if you compare the previous calculation and this calculation. So I'm going to use the same number, 9.545 times multiply by 10. That means 10 to the 23 atoms of hydrogen. Question? Everybody okay?
Yes.
Okay, good. So shall I stop today here and tomorrow I'm going to start empirical formula?
Yes.
Okay, if you have any question, please make appointment, okay, or you can ask me here tomorrow. But finish your homework, try to take the chapter 2 quiz. Okay? Thank you.
Thank
Thank
you.
I'll see you tomorrow.
See you tomorrow.